Assalamu alaikum and hello everyone. Welcome to the second and last class for magnetism. Today is 14th of August. So depending on whenever you're watching this video, happy belated Independence Day. Because most likely you're going to watch it tomorrow, which is 15th or even 16th. Anyway, this is a very important lecture and it's going to be hard. It's not going to be easy. So make sure you are attentive, and if you miss my word, you're not going to get this chapter. I can give you my word. If you don't try to understand it now, no matter which book you open, you're not going to be able to understand it because some concepts are just too confusing. I have been there. I missed one class at my teacher, and I tried to understand that topic from all the books I had, and I was not able to understand it. So pay attention, right? Anyway, we did some basic stuff on Wednesday, I believe. Today we're going to do heavy stuff. Let's start. Magnetism. So the new formula that I am gonna give you is gonna be right after I make this diagram. So you have two options. You can either make the diagram with me, or you can do it after I finish, and you can just pause the video. I am not gonna always say, okay, so now you can pause the video and note down. So it's completely up to you. Anyway, let's use some lines and make the graph. I mean, not the graph, the diagram. So this is gonna be a electronic balance, and it's a 3D diagram. We have a lot of things here, so let's make it. Okay. You can also skip the part where I'm making the diagram because I don't have the time to edit the video. So you can just skip it to whenever I am done. Okay, so now I'm going to use the pen to make the magnet. Okay, so here we have the magnet. This is called a horse hoe magnet, and it's like a shape like this, and the magnets are glued onto this shape, and it looks like this. It might be a magnet on its own as well. Okay, so it's like this. So it's a nice 3D shape. One of these is a North Pole, the other one is a South Pole. And like this. Using some black, let's continue, and we're done. All right, so this is the south, right? This is the south, this is S, and this is N. And it is placed on the electronic balance plate. And now this is the important part. So this is what this whole thing is about. We have a conductor. So this is called a conductor. It's a wire, or it can be an aluminum foil, it can be anything. So anything that conducts, usually it's a wire, and it is clamped. It cannot rotate or move in any weird way like in O levels. So this is the minus and this is the plus. So this is the minus and this is the plus. Okay, let me use a more vibrant color. Orange, yeah, plus, minus. And we have clamps here. This is clamp. Right? It has been clamped, meaning it cannot move. It is positioned like this and it is fixed. We can have readings here, and yes. Okay, so the formula I am gonna introduce you is FB is equal to BIL. Magnetic force is equal to BI and L. You know what is B? B is magnetic flux density, I is the current, L. Now, this L is not this length. It is the length of this L was 2 pi r just for the Ampere's law, right? I hope you guys remember Ampere's law. It was B is equal to, I'm going to add this later. So U naught I, and this was L, right? BL U naught I. So L here, L was 2 pi r, which was the magnetic field circle, right? 2 pi r. That was the length for this. But this L is the length of conductor, or the conductor that is exposed to the magnet. Just a second. So the conductor that is exposed to the magnet, like this part here. So yeah, that is L. Anyway, let's erase this and let's explain. Now, this experiment goes like this. We have a switch here. So the switch looks like this. We have a switch here, and this switch is either opened or either closed. And the fun fact is, when I have the switch in an open state, I am going to have a different reading. And when I have the switch in a closed state, I'm going to have a different reading. So right now, the switch is open, nothing new, right? I have a reading here that is 50 grams, let's say, right? So 50 grams, 50 G. But when I close the switch, right? When I close the switch, I am going to have a different reading, which is going to be not 50 grams. Now let's see if it's going to be more or less. Okay, the explanation. So let's use the Fleming's left-hand rule. First of all, we're going to use the conventional current. So the current is going to come here from plus sign all the way here, here. That is the current flow, right? The current is flowing from plus to minus. We're using the conventional current. So place your fingers in the positions. You know, the first finger is for the magnetic field, so north, south. The second finger is for the current. It's going to be over here. So it's like this, this, and this. This is your thumb, first finger, and second finger. So you're going to find out that according to this diagram, once the switch is closed, so let's close the switch in just a second. So let's close the switch. The switch is now closed, and we have, okay, so the switch is closed and the current is flowing. The force is going to go, the force is going to be upwards. So let's show that. The force is upwards. That is the force by Fleming's left-hand rule. Now, I want you to think for a second. If force is upwards, right? If force is upwards, what is going to happen? Is this reading going to increase? Okay, so we have 50 grams here. Now, I have a question for you. Is this reading going to increase or is it going to decrease? Think about it. I'm going to give you 5 seconds, right? 5 seconds to think about it. All right, I guess 5 seconds have passed. The answer to this is the reading is going to increase. You must be wondering why. Why is it that the reading is increasing? Force is upwards, right? So you would think that, okay, so if weight is downwards, force is upwards, then W minus F. Oh, so this reading should be lesser. No, that's not how it works. That is not how it works. Do you remember the scenario when a person is standing like this, right? And when a person is standing, you know that we have W acting downwards and we have N acting upwards. And I also told you something. This N is the thing that decides this thing, right? N is what causes the reading on the balance. Otherwise, why is it that when I'm in an elevator and let's say elevator is moving down, why does my mass go down? Why does the reading decrease, right? Why doesn't it stay the same? Because it's not determined by W. It is determined by N, or like I said before, Fs, right? This is determined by this. So imagine it like this. Because F is upwards, N is going to increase, right? N is going to increase, and by Newton's third law. So let's say before it was 50 grams, right? So let's convert that to force. I don't know how much that's going to be in the force, but let's say 10 newtons, right? So now because I have F here, it's going to be, let's say 15 newtons, right? I'm going to have 15 newtons here. What does that mean? If I have 15 newtons upwards, that means by by Newton's third law, there's going to be a force downwards as well, right? So this downward force is going to cause 50 grams to change to 75 grams. That's what happens here. So always remember that this upward force is what determines your weight. Anyway, let's write the definition. So I'm going to use the text to write it. You guys can write it with me because you're going to have time for that. Okay, so explanation. Let's do this. Explanation. It goes like this. Due to Fleming's, right, due to Fleming's left-hand rule, the force on the wire will be upwards. Therefore, due to Newton's third law, the force on the magnet would be equal and opposite, right? And opposite, which is downwards, right? So in the brackets, you can write downwards. And so the reading on the balance, right, on the balance increases. So it comes a lot in the past papers, and this is literally your answer, like copy paste. That's your answer. Trust me on this. This is your answer. It's a 3-mark question, and you're gonna get all your marks. Anyway, so there's another thing you have to know. If I make a graph, right? If I make a graph of F, of force and current, you're gonna get this. Obviously, assuming that other stuff is constant. So the greater your current, right? So if I increase this current a lot, this means that your reading is going to be even greater, right? And depending on the direction of your current, right? If this was plus and this was minus, this may not have been the case. Anyway, this is your graph. So reading on the balance, reading on the balance. Right? Let's change the size because that's too big. So current off, current on. So this is going to be 50 grams and this is going to be 75 grams. So change in mass is going to be 25 grams. And if I want to calculate FB, it's going to be 25 divided by 1,000, convert it to kilograms and multiply by 9.81. And you can find your force. We don't care whatever is the answer, right? So answer. Anyway, take a screenshot or note down. I would suggest you to note down. Don't rely on screenshots. Anyway, let's move on. Okay, now let's make another graph. This is the continuation of this. So let's make 2 arrows like this and another arrow like this. And for the second graph, we have an arrow like this and an arrow like this. Make your lines, it's going to be straight lines. I'm going to tell you what is here later. For now, let's just make the lines, and these are staying, right? So FB, FL. So obviously, assuming that other stuff is constant, the greater your length, right? So the greater length of wire, so imagine these were the magnets, the greater this L is, the greater your force, right? So the length of the wire in contact with magnetic field, the greater that length is, the greater your force. And this is external magnetic field, meaning B of magnets, right? So external magnet, right? External magnet field, right? Magnetic field. Anyway, now let me tell you another thing. When I say that there's force and there's current, this is current, and we're going to have some lines for force, right? So force, magnetic field, not a force. So this is magnetic field, right? So this is B, which is magnetic field. I is current, and you have to know that for you to have the maximum force, right? F max, the angle, which is obviously here, this angle between the magnetic field lines and the current, it should be 90 degrees, right? So F max is when this is 90 degrees. Theta is 90 degrees. What does that mean? That means that if I suddenly say, okay, so now my current is over here. So if this is your current, right? Let's see the color of, so if this is your current, right? If this is your current, that means that the force is going to be zero. Why? Because, I mean, they're parallel, right? If they're parallel, the angle is going to be zero, right? And obviously sine zero is going to be zero as well. So that's why we say F is proportional to sine theta. So depending on how different your angles are, max, right? Lesser, 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 zero. Max, lesser, 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 and zero, right? I hope that made sense. So we're gonna make a graph here like this and like this, right? And we're gonna make some readings here. This is for F max, right? So this is gonna be F max. This is F max, and this is theta. This is F. And let's make the angle. So this is 30, this is 60, this is 90. Then let's make a dotted line upwards and let's make the graph. So the graph is going to look something like this. So it's going to be a curve with decreasing gradient. So at 30, at around 30 degrees, right, we're going to have F max divided by 2. So this is going to be F max divided by 2. Now my diagram is not that accurate, so apologies, but yes, at 30 degrees, according to the actual graph, you should have F max divided by 2. Anyway, so F is going to be thus equal to, let's erase that. Let's just minimize everything, right? So, oh, that's messed up. Just a second. Let's just go back. Okay, just take a screenshot. I'm about to erase this. Okay, so that leads us to F is equal to BIL sine theta, right? Because I just showed you that force is proportional to sine theta, right? And thus, if wire is placed perpendicular to the field, F max, you're going to have maximum force, and that is BIL, right? Because we know that sine 90 is equal to 1. That's basic math. All right, so let's move on to the next thing. Okay, so if you did not understand anything, just go back, rewind the video, and watch it again. Okay, so B, if I rearrange this formula, I'm going to end up with B is equal to F over IL, right? And thus, I come to the conclusion of magnetic flux density or magnetic field strength, right? So magnetic flux density is, let's use green. So this is defined as the force acting per unit length on a current carrying wire placed perpendicular to the magnetic field, right? So some points here are crucial. That is perpendicular to the magnetic field, and obviously force acting per unit length on a current carrying wire. So all of these are important. All right, and the unit of that was Tesla. This was Tesla. And if they ask you define Tesla, so if they ask you define Tesla, you're gonna write, now pay attention here. You're gonna write a magnetic flux of 1 Tesla, right? So 1 Tesla, magnetic flux of 1 Tesla produces a force of 1 Newton, 1 Newton on each meter of wire carrying a current. So carrying a current of 1 ampere placed perpendicular to the field. Now, how it works is this is literally the same thing as this, except they have written the amount of magnetic flux density, which is 1 Tesla, and the force acting per unit length. You have to specify that a force of 1 Newton acts on each meter, right? So you have specified what force, what length, and what current, right? So a current of 1 ampere. And finally, the important point. And that's it. All right, let's clear this. All right, so that leads us to the next concept, which is force between two current carrying conductors. So this is an important concept, so make sure you pay attention because this is actually a tricky concept. So you have to listen to this concept with open ears and open minds. All right, let's do this. We have two wires, right? I have wire 1, I have wire 2. This is the same thing as when the right-hand grip rule, right? So this is the same wire as that. So obviously there's current in these wires, right? There's some kind of current here, and this current is I, right? So this is I1, and this is I2, right? So let's elongate these so I can do something that I want to do. And according to O levels, you know that if we actually made their magnetic fields, they would look like this, right? So they would look something like this. So something like this. This is O level. I'm not making it accurately, but that's what it looks like. So by right-hand grip rule, it's going to be like this. And the direction of current in both of these is the same. And you can see that these two are kind of moving towards each other. I think that's O level 2. So if the direction of currents is the same in both, they're going to move towards each other. So this is going to be F. This is going to be F. And yes, so it's going to have B1. We're going to have B1. So this is wire 1. And this is wire 2. Now, I need you to question yourself for a second. Ask yourself, this force, what is causing this force? Is this F1 or is this F2? Is this force being caused because of this magnetic field or this magnetic field, right? So if I were to mention magnetic field, this would be B1 and this would be B2, and both of them have combined together to form this. Otherwise, this is B1 and this is B2. So I can say that B2, right? So if I would make its magnetic field individually, it would look like this, right? So this B2 is actually causing this force here. Don't you think so, right? So this is B2, and B2 is causing this wire, which has a current of 1 ampere, to be attracted towards it, right? So I can say that this is F caused by this field. Now I'm going to get back to it in a few seconds. All right. So this F on 1, right? So F on 1. So it's going to be F1, but you know that F1 is not being caused by this, right? So F1 and F2. So F on 1 and F on 2. All right, so F1 is equal to B2 I1 and L1, and F2 is equal to B1 I1 and L2. Now let me explain you here. F1, meaning F on 1, B2, what is causing this F? The magnetic field of the second wire. That's why here we're going to write B2, right? But now, what about the second one? So F2, F on 2, it has its own current, which is I2, and it has its own length. But what is causing this force here? Well, B1. So B1 is causing the force here. Now, let's rearrange these formulas to this. So F1 divided by L1 is equal to B2 into I1. Now let's write it for the second one, which is F2 L2 is equal to B1 into I2. Now, this is where we're actually going to use something we learned in Ampere's law, the thing I taught you at the beginning, and it's going to be this. So you know that BL is equal to U naught and I, and if we rearrange this, it's going to look like this. So B is equal to U naught I divided by 2 pi r. Now, what if I say this is for 1, right? This is B1 and I1, right? And this is for 2, U naught, I2, and 2 pi r. Now we're going to substitute this B1 and B2 into their respective places, right? So this is B1 and this is B2, right? So let's substitute these things into that. Now let's use a uniform color. You're going to see why. So F1 over L1 is equal to U naught I2 divided by 2 pi r and I1. Let's do the same thing here. Let's use a brown color. So F2 divided by L2 is equal to U naught I1 divided by 2 pi r and I2. Look at these formulas again. Does this part look different or does it look the same? Exactly, it looks the same. What does it mean? It means that F1 divided by L1 is actually equal to F2 divided by L2. And this is an actual fact that we have just proved with you guys. Let's circle this. If you didn't get this, rewind and look at it again. Basically, we have just proved that if we have currents that are over here, we have forces and all, F1 over L1, F1 over L1, right? So this is L1 and this is L2. It's going to be equal to F2 over L2, right? Let's write that. Equal. And by the way, this came to prove in the paper, right? So this came to prove in the paper, by the way. Came to prove CAIE. So make sure you memorize this. You don't want to miss it. All right, take a screenshot, note down, and let's move on to the next concept. All right, let's make two magnets, north and south. So two magnetic poles to be precise, and a portion of south. I have south, I have north, right? So I have south and I have north. And I have a rather interesting thing in between here. Let's make that. So it looks something like you did before, doesn't it? Let me show you how. So let's erase this part here, and we're going to have a plus, we're going to have a minus. Let's use black. Okay, so this is plus, and this is minus. Okay, let's fix it up. All right, so this is going to be minus, and this is going to be plus. Let's make a normal line in between, right? Let's use a very thin line to show the normal. So this is the normal line. And with an arrow, I'm going to show that it is actually rotating, right? So it is rotating like this. Let's see how. So we're using conventional current again. Current is going to flow all the way from plus to minus. So current is flowing like this. So this is I, and this is I. And so I can show that the force, using the Fleming's left-hand rule, I can say that force is inwards here and force is outwards here, right? Force is outwards here and force is inwards here, doesn't it? Isn't it? All right, so this is going to be A. This length is called A, and this length is called B. So this is B and this is A. So let's discuss moment due to a couple. Doesn't it look like the moment due to couple? Because force is going inwards here and it's going outwards here. So it is rotating like this, right? So that's called the moment of a couple, right? We did that in AS. So let me fix this direction so it's going like this actually. Anyway, so the formula for this is F into D, right? It's F into D. F into D. And what is F? It is BIL. I hope you did not forget it. What is D? D is A, right, and B. So L and D is A and B. So BI is actually, we're going to have A here. So length is A, right? Length of the wire. So now you saw that L is actually this, and D, distance, is actually B, because this is the distance between the forces, right? That's what we did in AS, right? Force, right? Force, and distance. Don't forget AS, come on. Moment due to couple. If you don't get this, revise the concept of moment due to couple. So this is B. By the way, if I multiply A and B, can I say that this is the area A? I mean, yes, if I multiply A and B, I'm going to get area A, right? A, I'm going to get A. This is going to be A, and A is my area. So now it's going to turn into area A. So I'm going to get BIA. Now, what if I say I need moment due to n turns? So now it's not just one turn like before, it's going to be more than one turns. So what you're going to do is you're going to multiply this whole thing with n. So multiply this with n and write it here. So n IAB, or I think you can remember it like this, NIAB, or you can write it as BINA or ANIB, or yeah, or ABIN. It's your choice. I wrote it NIAB in my notes. You can write NIAB too. Anyway, I hope that made sense. You can rewind it if you did not get anything. Let's move on to the next concept. Okay, so now let's discuss force on a moving charge, right? So force on a moving charge. So force on a moving charge. Okay, let's write the formula for force. F was BIL sine theta, right? By the way, what is the formula for current? Current is equal to Q divided by T, right? So charge over time. That's a basic formula. So let's substitute that over here and let's write Q divided by T. And let's just write the other thing as it is, B. Now tell me one thing. What is length divided by time? It is velocity, right? So length divided by time is velocity. So I'm going to get F is equal to BQV or BVQ, right? So BVQ sine theta, and that's a new formula. Don't forget this. This is another derivation of formula. So F is equal to BVQ sine theta. Okay, now let's make a magnetic field. By the way, in the paper, they're not always going to make crosses and dots, right? Not always. They can make it like this, and they can say into the page, right? Into the page. So they're not always going to make these crosses and crosses because they ain't got time for that, right? So it's not always going to be crosses and crosses and crosses. They can just make it shaded and they can write into the page. So be prepared for that. Okay, so I'm going to have a charge coming in from here. So this is charge and this is minus. It's going to be minus, right? It's going to be minus. And it's coming in from here, right? So this is the direction. By the way, what is the direction of my current? Think about that for a second. Is my current going to be towards the right or towards the left? Because obviously, magnetic field is into the page, so you're going to place your finger like this, right? But where do you put your second finger? You have to decide that. If your answer was left, you're correct. Why? Why? Because we use conventional current. So if this was plus, I would say current is here, right? If the arrow is here. But because plus is always in opposite direction, I'm going to say that current is towards the left. I repeat, Since this is minus and this is not plus, and we use conventional current, and that is always the direction of plus. So yes, that's why I do the opposite. So current is here, magnetic field is into the page. So the force is going to be downwards, right? The force is going to be downwards. Okay, but there's something that actually happens here. Let's observe. The force is downwards, but velocity is like this, right? So velocity is, can I say this is velocity and this is force, right? Doesn't this remind you of something? Velocity, force, 90-degree angle. If you said circular motion, that's amazing. If it did not say circular motion, that's not amazing. Let's see how. How in the world do we get circular motion here? Let's see. So it's not exactly circular motion, but it is gonna start to move in a curved track. And there's a reason for that. So this thing right here, right? So this is gonna be the direction of velocity, right? So this is gonna be the direction of velocity. Velocity here. And here in the middle, the force is gonna be towards the center, which is downwards. And because velocity and F are having a 90-degree angle, it's gonna move down. So now velocity is gonna be here, which is over here, right? But velocity when it is here, when velocity is here, look, when velocity is here, what am I saying? Think again. Velocity has changed, right? Velocity is here now. What does that mean? That means that minus charge is now moving downwards. So the force is not gonna be downwards anymore. The force is gonna be in a different direction. So if current is upwards, why? Because minus is moving downwards. So I is going to be up. Let's use Fleming's left-hand rule. So current is upwards, and my thumb is going to be towards the left. So force is going to be towards the left, right? So force is going to be towards the left. And it's going to repeat, the same process is going to be repeating itself. And we're going to end up with this. So V is going to be here, and force is again going to be towards the center. All right, force is going to be here, and the same thing repeats. So same thing repeats. And over here, force is towards the center, and velocity is upwards, right? And we're not concerned about what happens next. That's none of our concern. But we're only concerned about how did it make a circle. Okay, so this is V, and this is F. Right? I hope that makes sense. So logical answer, why is it moving in a circle? Right? So why is it an arc of a circle? There's a reason behind that. Because V and F are at 90-degree, or in other words, they consistently remain 90 degrees. And because they're consistently 90 degrees, let me make that 90-degree angle so you guys can see, right? So 90, 90, 90, and 90. So all these 90s are because they are consistently 90 degrees, right? So they're consistently 90, and that's why it's moving in circular motion. That's a secret. So how did we get centripetal force? Well, let's talk about that. Magnetic field. You know what I'm about to write. Magnetic field provides FB, or centripetal force. So I can say that FB is FB because I can get an equation here with QBD is equal to MB squared over R. So we can cancel that, and I finally get R is equal to MB divided by QB. And I'm going to get another derivation then. I'm going to ask you in the paper. So remember this. What's important. Okay, so note it down, and get it, fine, that makes sense. I have a question. Why is that happening in this situation right here? I have plus, I have a plus here. I have a minus here, so this is plus, and this is minus. So I have a charge here. Let's make a circle. Let's make a circle here. It's going to be minus, right? So a negative charge or an electron is moving towards this direction, right? Like this, right? Like this. Now the question is, why doesn't this enter circular motion, right? I mean, it is also in an electric field and it has there's a magnetic field too, probably. Well, that's because, look at this. Yes, okay. At the beginning, the force is upwards and velocity is here, but does it remain consistent? No, because the force is here, but now the velocity is here, right? That's not 90 anymore. And here it's even worse. Velocity is over here. So force and velocity are not consistently 90 degrees. So not consistently 90 degrees here. So that's why we're not going to get a circle. So not a circle. All right, let's do a question here now. So at a speed v, it takes time t to make a circle. If v is doubled, calculate how much time it would take. The question is, at a speed v, it takes time t to make a circle. They're talking about the same thing that we just did. Now they're saying, what if we double the velocity? What is going to happen? You have a few seconds to answer this. Pause the video and try to think about it. I'm giving you a few seconds to do this, and then I'm going to continue with the answer. Okay, so I hope you have concluded with an answer. The answer is, it takes lesser time, or so I wanted to say, but it takes the same time. As when the speed doubles, I'll write that in caps, the radius also doubles. That's it. Why? Because radius is proportional to velocity. How can I say that? Well, I think we just derived a formula with you guys. And if I derive something, that obviously means that it has some kind of importance, right? The charge is same, magnetic field is same, mass is same, everything is same. Velocity is doubling. What does that mean? R is proportional to V, as this is constant, right? This is constant, so radius is proportional to velocity. And that is why if I have double R, I'm going to have double V, isn't it? Right? So V doubles, so R doubles. Okay, so note that down, and I'm gonna give you actually a few seconds, and then we're gonna start the next thing. And this time, this is gonna be a hard concept, right? So this is gonna be a confusing concept. So get ready for some confusing stuff. All right. Okay, so let's do this. All right, so we're gonna discuss the Hall effect now. The Hall effect goes like this, right? So it's also a Hall probe. You can call it whatever you want, but this thing that we're studying right now, this is called the Hall effect, the Hall effect, right? So Hall effect. Okay, let's just write that later. I'm gonna make a cuboid or a cube, right? So cuboid or a cube, it's gonna look like this, right? So cuboid, and it goes like this. and like this. It's obviously not a proper shape. I'm just doing it really fast, not caring about proportions. Proportions are off, but that doesn't matter. And we have a wire here that connects this part and this part with a voltmeter to measure the voltage that we're trying to measure. This is also a basic structure of Hall probe, right? Let's make a circle. And this is the voltmeter. So it's going to have a V sign here. Now, I have this side positively induced. Let me make positive with red. All right, so let's show positive with the red. Okay, I cannot show that in this shape. Let's just do it like this. All right, so this is gonna be plus. All right, so plus. So this is plus, and this is gonna be minus. So we have induced each side with a charge. This is minus. This is plus. But now I am actually sending an electron beam from this side. However, before sending this electron beam, I have to tell you that the magnetic field here is into the page. So like this, front to back. So this is the magnetic field. So you can imagine it like this. So from this point to that point, that is the direction of B. But I'm not going to show it here. I'm going to show it on the left. So that's the direction of B. So front face to back face. Let's write that down. So front face to back face. Now, since this is an electron beam, the current is going to be towards the left. No, it's going to be towards the right. So current is towards the right, right? So I is right, not left, right? Anyway, this is distance t, right? This is t. Let's show that with green. This is t, and this is d. This distance is d. So from this is d, and that is t. So that is t, and this is d. Okay, much better. All right, and this would be area A, right? So this is area A, right? Okay, now that we have sent the electrons and they have entered this region, let's show the electron, right? This is the electron. Now, where is it going to go, right? Where in the world is it going to go? Magnetic field is into the page. Take your left hand with your first finger, make your finger, point your finger towards B. And since current is towards the right, your thumb is going to be upwards, right? Your thumb is going to be upwards. So electrons are going to go up, right? Electrons are going to go up, and electrons are actually going to induce this negative charge. So I should have mentioned it before. Basically, this negative charge and this positive charge, it comes later. At the beginning, we just have this cube. B is inwards, electron beam is over here. It's acting here. Now, because the force is upwards, right? Because the force is upwards, you don't need to erase that because, yes, so because the force is upwards, magnetic force, electrons are going to start collecting over here. And that's how we're going to get that negative charge, right? So let's go back and let's bring back. Now, listen, when I say that I'm getting a negative charge here, what does that mean? That means that this is going to become plus, right? So this whole side is going to become positive because electrons moved up and this got induced with positive charge. Now let's go back. And I want to ask you guys something. Now that this charge is negative and this is plus, what about the future electrons, right? What about the future electrons? Can I say that they're going to face two forces, right? This is going to be the magnetic force. This is going to be the electric force. Can I say that? Why? Because minus attracts to plus, right? And magnetic force is due to Fleming's left-hand rule, we know the electron should go up, right? But now, because there's a lot of electrons here, there's a lot of plus charge here, that means that we have an electric field as well, right? So we have electric force that is causing the electron to go downwards too. So now listen, there comes a point, when this force becomes equal to this force. At this point, no electrons are going to go up. Why? They're going to stay here. So if we keep sending electrons, there's going to be a point when electrons are not going to go up because magnetic force is canceled out with this force. So electrons are literally going to stay here. Literally. They're not going to move up. They're not going to move down. So at this point, no electrons go up, right? They're not going to go up because these two forces are equal. And this is that point when we actually say that QVB, which is magnetic force, is equal to QE. Conclusion is QQ cancels out and I get this formula, which is E is equal to VB, or V is equal to E over B, right? So these, I get these two. All right, let me introduce to you guys the concept of Hall voltage. So this voltage, right, this voltage that we're about to measure in this system, which is a Hall probe or something similar, this is called the Hall voltage. So what is the formula for electric field and voltage? That is E is equal to VH divided by D, right? So can I say that E is equal to E? So I'm going to equate 1 and 2, right? 1 is equal to 2. So at the end of the day, I end up with VH divided by D is equal to VB, right? That's what I get. Now let's continue the derivation over here. So yeah, let's do this here. Okay, let's write it in a neater way using a green color. So we're continuing this part over here. By the way, make sure you know that this V is actually the velocity. It's not something else. All right, so this is actually the drift velocity. So VH is going to be equal to BVD. And since we're dealing with particles, charged particles, electrons, etc., this V is actually drift velocity. AS, come on, AS, drift velocity. Now, in AS, you studied another formula, which was I is equal to NAVQ, right? I is equal to NAV or NACOR, your choice of remembering it. So drift velocity is going to be equal to I divided by NAC, right? NAC, that sounds cool. So NAQ, NAC. Now, I'm going to substitute this into this, and I'm going to end up with VH is equal to B. And let's write that all in red. I divided by NAQ. And D is going to come here. Now, what is A? A is area, right? There's a reason why I said that this is A before, because I know that A is what? T multiplied by D, right? So I can say T into D. D is this distance, T is this distance. So I can say that VH is equal to BID divided by N D T Q. And I can cancel out D and D. And finally, I end up with VH is equal to BI divided by NTQ. And this is an important formula for drift velocity, so make sure you remember it. It may come to proof, by the way. So yeah, I hope that made sense. A little recap. Um, we send electrons due to Fleming's left-hand rule. Magnetic force is going to be upwards. Electrons are going to gather up here. Minus charge is going to induce a positive charge here, and electrons are going to get attracted to plus. So this is Fe, force due to electric field. This is Fb, force due to magnetic field. They are going to become equal at one point, right? And at that point, no electrons go up, and all of this happens. I hope that made sense. All right, so we have done something that's actually hard, by the way. Now, I want you guys to understand something. I can also say that VH is proportional to B, right? So if I increase this magnetic field, right? If I increase this magnetic field, right? So VH is proportional to B, something I just derived from here, assuming that everything else is proportional, right? So if I increase B, VH is going to go up as well. That's a fact. Anyway, note this down and let's do the next thing. This is also used in the calibration of the Hall probe. You might have VH and B for one value, right? And let's say you have VH and you want to find B, so you would use this formula to find any one of these. Okay, so the next thing we're going to do is we're going to make a coil, right? I hope everything has made sense so far. If you don't understand, you can watch it again, or you can just message me, right? You can just message me privately and I'll answer you. Make sure you revise, by the way. I'll tell you something at the end of this video. It's something that all of you have to hear, so make sure you stick till the end. And yeah, definitely finish this video during the weekend. Do not leave this for Monday. I am warning you, do not leave this for Monday. This is so important that if you don't do this now, that's like now or never. That's true. Now we have, by the way, in your notes, make a heading of Hall probe and Hall effect. So Hall probe in brackets, Hall effect for the previous thing we did. Right, so the previous thing we did was Hall effect, Hall probe, and in the brackets, Hall effect. So this is millivoltmeter. This is a Hall probe, right? And we get a graph here. Now this graph is tricky, so be very, very, very attentive because it's actually hard. Now, I'm not moving anything. Everything is static. Nothing is changing here, right? So this is going to be off. Let's make it better. Let's make the graph a bit more handsome. It looks really ugly right now. Okay. All right, so. All right. So at one point, we're going to turn the Hall probe on, and at another point, we're going to turn it off. My question is, what is it going to look like? So because of this coil, there's going to be a magnetic field, right? Because of this coil, there's current flowing. Obviously, there's going to be a magnetic field, right? By the way, I forgot I have to fix one thing. We're not turning the Hall probe on, we're turning this switch on, right? So we're turning the switch on, and this reading is on the Hall probe. So when we turn this on, when we close the switch, right, there's going to be a reading on Hall probe. The graph is going to look like this. Why? Because nothing is moving, nothing is changing. If I have an angle, right, it's going to stay at the same angle. Because everything is static. Everything is just standing here. So if I have a magnetic field, it's going to be constant. So because of that constant magnetic field, which is, VH proportional to B, I'm going to have a straight line. That's it. That's easy. Let's minimize this and let's move it over here. Now the next situation that is actually going to be harder, comparatively harder. So I am going to make a wire, right? This is a wire. Oh, so we do, let's make a wire. So this is a wire, right? This is a wire. We have current I in it. This is I. Oh, not the arrow. So we have current I in it, or this is a wire with current I in it, and I have a Hall probe here, like this, right, like this. So whenever you're doing a paper P5 and you want to show the Hall probe, it's going to look like this. This is millivoltmeter, and yeah. So we are moving the Hall probe away, right? So we're moving the Hall probe away, and we're going to make a graph. So think about it. What is the graph going to look like? What is the graph going to look like? I have VH over here. Right? I have VH on the y-axis, and I have T on the x-axis. Now, I am moving this away. So obviously, more the distance, lesser the VH, don't you think? Because magnetic field is here, and obviously with distance, magnetic field is actually going to get weaker. So I'm going to get like a graph like this. Right? Eventually, it's going to go to 0. We're actually going to touch it, right? Right. So let's touch it. And like this. So that's what we're going to get. It's going to touch here eventually, right? So it's eventually touching here. Okay. So this is 1, this is 2. So at T is equal to 0, VH is max, right? So this is VH max. And because we know that magnetic field is 1 over R, and VH is also 1 over R, because B and VH are proportional to each other. How did I say this? Well, B is equal to U naught I divided by 2 pi R, right? Basics, right? Basics. All right, note this down, take a screenshot. I think this is easy too. So until we actually understand it, it's always going to be hard. When we understand it, it's going to be easy. All right, now I have to admit, this one is tricky. All right, so pay attention, listen with open ears. Right, like this is actually going to be tricky. Now, I have current I here, and I have a Hall probe over here. It's like this. And I have a normal line here, right? So I have a normal line here, and it's like this. And we're actually rotating it here. So it's rotating like this, right? So like this. Let's use a thicker line, right? Like this. And obviously we know at time 0, VH is going to be 0, right? Because of the angle. Now, I told you guys something that day. If this is the surface of my Hall probe, let's say, right? Like this is like this. So the angle, it makes a lot of difference. You're not supposed to make this. So if I am sending this at this angle, and at this angle, at this angle, it's going to have different values. Now, magnetic field is like a circle, right? So it's obviously when I rotate this, the angle is actually changing, right? The angle is changing. And because the angle is changing, and I think I mentioned this before, one of the magnetic factors is proportional to the angle. So if I have a 90-degree angle, that's going to be the maximum. So it's going to turn out to be a sine curve. So it's easy to just memorize this data, but it's not preferable. Make sure you try to understand why in the world is this happening, because that's what's going to make you successful in physics. So we have started at a point where VH is 0 because what is the possible reason for that? Because the magnetic field and that thing, right, that surface was parallel, right? And when it is parallel, there's obviously not going to be any voltage flowing there, right? I think the thing that's similar to the force concept, let me recall that thing. So when I made the magnetic field and I showed you that current is flowing in that direction, there's not going to be a force. So something similar is happening here. For you to have a VH, it should be making a 90-degree angle. So you get a sine curve. You get a sine curve. And this is a proven fact. Anyway, those were the graphs. Make sure you memorize them because they are going to come in paper. And yes, let's do the next thing. We have less stuff left to do, and we're going to be done. All right, so now let's do the next thing. I have a question for you. When we compare metals and when we compare semiconductors, so metals, right, and semiconductors, right? Which one of these is going to have larger VH? Think about it. So I am using this as that cube, right? So as that cube, right? I'm using this as a cube. My question for you is, out of these two, which one of them is going to be able to get a larger VH, right? Which one of these? Pause the video, think about it, and answer the question. The answer is semiconductors. I know you're confused how. You were obviously expecting, I bet that you just answered metals. 100%. Because we assume that the more electrons we have, right? The more electrons we have, the larger the voltage. Well, that might be true in some cases, but not here. Not here at all. Mark my word, not here at all. Because, tell me one thing. Which one of these has more electrons? Metals, right? So I can say that number of charge carriers is more, right? N is greater, N is lesser. Now let's prove this using the formula. So VH is BI divided by NTQ. That's true, right? BI divided by NTQ. Now, BI, TQ, everything is constant. VH is inversely proportional to N. And that's my proof for you. And that's exactly why metals have lesser VH. Semiconductors have greater VH. I hope that made sense. I'm clearing this now. All right, so question. Let's do a question. So we have this cube here, right? We have a cube here that I made in a very bad way. We have a voltmeter, we have a magnetic field that's acting into the page, right, over there, and we have a positive charge carriers. But we have them later. We did not have them before. Let me show you how. So at the beginning, we had an electron beam, right? And the question goes like this. Let's write it in the text. So if the electron beam is replaced with positive charge carriers moving in the same direction. State and explain the effect on the polarity of VH. What's the answer? Obviously, you're going to think it's going to be different. Now, pause the video and think about it. When we had electrons, what happened? upper plate became plus, lower plate became minus, right? Upper plate became minus, lower plate became plus, and we ended up with something, right? What's gonna happen now? What do you think? The answer is there literally is gonna be no effect. Why? Well, upper plate becomes plus. Why? Because force is downwards, right? So the charge carriers, oh, let me fix it up. Using the Fleming's left-hand rule, these are positive charge carriers, meaning the force is going to be downwards. Current is here. So plus is going to get piled up here, right? This is going to become minus. Isn't that the same thing, right? Except before we had electrons that went up, but now we have pluses that go down. So it's literally going to be the same thing. And eventually that is going to become Fe, right? And this is going to become Fb, and they're going to become equal. Now the question was explain the effect on the polarity of VH, but this is minus, this is plus, no effect, right? Same, because this time plus goes down. Yes, if it was like this, then it would be different, but it's not like this, it's like this, so it's going to be the same. So simple answer is going to be this. Positive charge will flow downwards. The upper plate will be induced with negative charge, and the lower plate with positive charge. So you might want to change the positions, and you want to say that you want to start with down lower plate because that's what happens at the beginning, right? And thus there will be no effect on the polarity of VH. So to make the answer better, start with the lower plate first because that's what's happening first, right? And it's going to stay the same. Anyway, and we are at the last thing now. So I hope all of this made sense, and let's do the last thing, right? So note this down. Okay, so I'm about to clear this completely, and we're doing the last thing, which is the velocity selector. So this is called velocity selector. So this is a kind of confusing concept, right? So this is plus, this is minus. The field is inwards, right? So magnetic field is inwards, and we have an electron that is having Q and V, and it's traveling here, and at a speed V, it passes straight, right? Undeviated. Now my question for you is, what happens when 1, 2, and 3? Let me tell you what. So now we have 2V m minus q, right? We have V m plus q, and we have V over 2 m and minus q. So this is minus q plus q m v 2v v over 2. Change, pause the video and start thinking about it. All right. So now we have double the velocity, right? Mass and minus q. So this is negative charge, right? So I believe it's the same because it's an electron, right? So we're using an electron and it's of minus q. Anyway, minus q is going to be attracted upwards, right? So minus q is going to be attracted upwards. So I can say that Fe is going to be up, right? Fe is going to be up, and Fb is going to be, let's see what. So because this is minus q, meaning it's an electron and the direction of current is left, so use your fingers and you're going to end up to a conclusion that is Fb is down. So Fb is going to be down. Now, 2v, velocity is being doubled, right? Velocity is being doubled. What does that mean? Fb is bvq. So if velocity doubles, I mean, qb, the magnitude of qb are the same. Velocity doubles, so this is going to double too. So since velocity doubles, Fb doubles, right? Fb doubles, Fb is going to become greater than Fe. And what does that mean? It's going to go down. It's not going to go straight. So the answer here is going to be down, because magnetic field is acting downwards and Fe is acting upwards. All right, let's look at the next situation. V, M, and plus Q. Okay, so this is plus Q now. By the way, maybe I should not have written this as an electron. Let's just write it as a particle, right? Because you guys are going to get confused. So because it has Q, that's why I was so slow when I was reading this, right? So this is particle and this is Q, M, and V. Now, we have plus here, right? We have plus here. We have V here. We have M here. What happens? Since this is plus, it's going to get attracted downwards, right? I believe magnetic field is going to be upwards. So Fb is up. Fe is down. Everything is the same, right? Everything is the same as before. So Fe is going to be equal to Fb, right? And they canceled out. So this one is going to be undeviated. Undeviated. Now you know that velocity is proportional to magnetic field. So you should know now that if magnetic field decreases, electric field is going to be greater than magnetic field, right? Fe is going to be greater than Fb. And because of that, it is minus Q. It's going to be attracted to plus. So it's going to go up, right? Up. It goes up. And that's pretty much it. So yeah, since this is minus Q, Fb is downwards, Fe is upwards, and that's it. As easy as that. Right, anyway, let's erase this, and that's it. That's it. Note this down. I hope no one has a confusion. All right, everyone. So we have officially finished magnetism, but there's one more thing we have to do, which is magnetic resonance image. We're going to do that on Monday, along with the beginning of electromagnetic induction. Thank you very much. I'll see you all on Monday. Have a nice weekend, and let's continue with zeal and zest. We're going to work even harder. I have my exams coming. I'm still going to give it my all. The speed is going to be faster. So I hope you understand. And I just have to say one last thing. Even after the session ends, me and Fuzzle, we're going to be there for you. You can ask me anything you want, even after the exams. You can send your questions like literally anytime. That's something that I learned from my school life. The teacher doesn't love you as a student because you pay him money, but because you are his student. Even if you stop paying him fees, even if you finish school, that teacher is still going to be something important to you. And I think it's the same here. So thank you very much. We have 1 month left. Let's spend that last month with everything we have, and let's never forget that we did this together. Thank you very much, and Allah Hafiz.